and figure out the online mic issue. So Yaz, did you write this link down? All right. If anybody needs the link, Yaz has it. You got a 404? Is it, are other people getting 404? Did it work for anybody? Okay, it worked for people, so it might have been a typo. Make sure you do, it's case sensitive, I believe. Do we have the mic issue worked out? Did it light up green? Then I think it's working. Or you might have to switch which mic it's using. I did not do that. Okay, I'm going to move on. Okay, so the agenda for today. So I'm going to go through a quick introduction, which was supposed to end around now, but we started a little late. Then Bobby is going to go through the gem5 standard library. So this is a relatively new, as in within the past year, feature we've added to gem5, which we hope is going to make gem5 a lot easier to use. This is essentially just a much improved Python library for gem5, which Bobby will give an introduction to. And then I'm going to come back and talk about how you can extend gem5 for your new models, because that's what everyone wants to do with gem5, which is add new models to it so you can do your really cool research. So I'll talk about that after Bobby, and then I'll end in the last 30 minutes or so talking about everything else with gem5. I'll kind of touch on a bunch of the models within gem5, and I won't go into too many details about how to use them, but hopefully give you some pointers on where you can find more information. And then, of course, this afternoon, we have the gem5 users workshop. So I hope you stick around to hear about all the cool things that people like you are doing with gem5 this afternoon. Are we good on the mic? Great. Okay, so let's start with an introduction to, before that, any questions or anything? Any logistical issues? Any more logistical issues? Okay, great. So I'm going to quickly talk about how to get gem5, although I'll caveat this with you probably don't need to do this if you're using the code spaces. Everything's already there for you in the code spaces. So to download a gem5, you would use these things. So we would clone the gem5 repo, and then you can build gem5. So let me talk about these real fast. So we use Git as our version control system. If you're unfamiliar with Git or want to know lots and lots of details about Git, even if you are familiar, the Git book is a really good resource here. The main gem5 location, the canonical source for the repository, is on googlesource.com, not GitHub, although the GitHub is mirrored like every 15 minutes. So if you download it from GitHub, it will work, but that's just not the way if you want to contribute back, you need to use this Google source repo. There are two different branches for gem5. One is stable and one is develop. So stable will track the latest release of gem5, as well as any bug fix releases that we do. And so that updates once every few months, or maybe a little bit more frequently for bug fixes. Develop, on the other hand, is updated like daily, sometimes many times per day. So if you need the bleeding edge for some reason, if there's some new feature that has just been added, use develop. But I would suggest for the most part, for research-wise, build off of stable instead of off of develop. Okay, so building gem5, again, we'll do this a little bit later. You don't have to do this right now in the code spaces because we provided you with some pre-built gem5 binaries, which Bobby will talk about. But to build gem5, so we're going to use scons is our build system. It's kind of like make, but a lot more confusing and different and harder to figure out. But that's what we use. Then what you want to build is a parameter that you pass to the scon script. essentially. And this is a relatively complex little parameter. The build is the directory you want to build in. The second term is the particular target default options you want to have. So in this case, there's a file in build ops named x86, which has the defaults for this build. And then gem5.opt. Gem5 is the thing we want to build, the gem5 binary. And then .opt is some option of how you want to build gem5. Do you want to build it in debug mode? Or opt is optimizations with debug flags, or fast, which is optimizations and no debug flags. We usually use opt while developing because it's pretty fast, but still allows us to debug our code, and then fast for production. But we're going to skip all that for now and use code spaces again instead. So again, here's the link. Hopefully everybody has gotten that. So when you join the classroom, it ought to give you something that looks like this. So some kind of, it'll create a repository for you. It'll look something like this. Then you can click this code button. Then the code spaces. I guess I have circles. And then create code space on main. Pick the drop down. Click configure and create. And then select 16 cores when you do that. If you don't select 16 cores, then it's going to take you like half an hour, 45 minutes to build gem5, which we're going to do a little bit later, and that takes too long. But 16 cores will do it in about 10 minutes. I'll leave this up for a second. Questions? Most people able to do this? If you already created your code space because you're ahead of the game, you can switch to a different machine type pretty easily. So after that, it should just pop up something that looks like Visual Studio Code. And then this code space comes with a bunch of stuff. So this is all the materials and everything for actually the whole boot camp that we're going to be running this summer, as well as gem5 resources and other things. But this gem5 directory is where the gem5 source is. Okay. Anybody having trouble getting code spaces going? If so, just kind of raise your hand and someone will get up and help. Okay, so let me talk briefly about why we're doing this to kind of set a little bit of context for some of the stuff we'll be talking about gem5. So I really like this picture from Lieben's book about computer systems research. And one of the key things that we're going to do is we're going to design some experiment and then run some kind of model and measurement to conduct that experiment. And running computer architecture simulation comes in. So there's lots of different kinds of simulation that you could use for different purposes. So we'll talk some about functional simulation. In functional simulation, we are simulating programs correctly, but there's usually no timing information. So a good example of this would be virtualization platforms like QEMU. This is often used to validate the correctness of compilers or new ISA extensions, but probably not very useful for evaluating the performance of some kind of new architecture. gem5 can be used as a functional simulator if you run in atomic mode. There's also instrumentation-based or trace-based simulation. In this case, you can either use things like binary translation or traces to drive it. And this works well, especially if you're looking at one single component, say like the number of cache misses on a new cache design. But if your performance depends on the order of execution, this isn't going to work for you. So with a trace, you only have one order of execution. But if the performance, say you have a multi-threaded application and the performance of one thread makes a different ordering between the other threads, then trace-based isn't going to work because you're not going to be able to pick up on that potential different ordering. So things like PIN, CMP-Sim, and lots of other simulations fall into this trace-based category. And then there's execution-driven. So in this case, functional simulation and the timing are done together, step by step. And so it's like when you do an add, you only do that add at the time it would actually be done. So gem5 is like this as well as many other simulators. And we call this either execute and execute or timing directed. And in this case, we can pick up on the differences with, say, different thread interleavings and things. So another kind of simulation that you'll hear a lot is full system simulation. So at least for my definition, we kind of call this as simulation where all the components are modeled with enough fidelity to run unmodified applications. So you can kind of think of this as like bare metal simulation. So you can run something, say Linux, that would run on a normal piece of hardware and run that in your simulator. So gem5 is a full system simulator. You can boot unmodified Linux and just run that and run any application you would run under Linux. Then you can often combine these kinds of things together between execution-based and full system, etc. So let me give you a bit of nomenclature because I find this to be quite confusing sometimes. So we have, this is our traditional layers in a normal unvirtualized system and a virtualized system. So you have a host that you're running on top of, that's the hardware. And if you run something on top of the hardware, that's native execution. If you have a hypervisor, if you're running in a virtualized environment, you have a guest operating system that's running on top of your hypervisor. Right? This is just simple operating systems concepts. So if we look at simulation, we can use some of these same terms. So the host is the actual hardware you're running the simulator on. The simulator runs on the host and exposes some kind of hardware to the guest or the simulated system. The guest is the code running the simulated software. So if you're running Linux on top of gem5, Linux would be your guest. We have the simulator code, which is executing natively on the hardware. So if you talk about the performance of the simulator, you're talking about the performance of the simulator code compared to the simulated performance of the simulated application. Then we have the guest code, which is the benchmark or the workload or whatever you're running on top of gem5. Does nomenclature make sense? Great. So again, as far as performance goes, if you're talking about the simulator's performance, this would be how fast is gem5, whereas if you're talking about the simulated performance, this is how fast the benchmark is running on your system. Okay, so now I'm going to talk briefly about gem5's architecture, and we'll talk a lot more about this as we go through the tutorial. So gem5, every model in gem5 is what we call a SimObject. This is the things we're going, you build on top of SimObject to build your models. So most of gem5's models are written in C++. So these C++ objects will all inherit from SimObject. And these are the things that represent some physical component in the system. You can see a few of these many SimObjects that we have. I think we have like 400 or something in gem5. And if you build a new model, you want to build off of a SimObject. So this is where things start to get a little bit confusing. So we have our models in C++, the SimObjects, and you can find those in source. Then we can define parameters that you want to set on these models. So a cache, maybe it's the cache size or the latency, etc. You can define those parameters that you want the user to set on your model via this Python wrapper, which is also in source. We can call this a SimObject declaration file. And then once you've created a model and defined the parameters you want the user to set on that model, or you want to change on the model, now we need to create an instance of that model and connect it to our simulation system and then simulate it. So that instance is some particular choice of parameters for that experiment that you want to run. And you do this either by using the standard library, which Bobby will talk about, extending the standard library to specify certain parameters, or specifying them in your Python run script. And again, we'll see more of this in a minute. Okay, and the last thing I want to talk about, I think it's the last thing about gem5's architecture, is that gem5 is a discrete event simulator. So the way it works is gem5 has an event queue, and then there's a loop that pops the earliest event off of the event queue, in this case, say event 10. It executes that event. During that event's execution, it might create other events and put those events on the event queue. So in this case, event at time 10 created a new event for time 55, and then so on and so forth. So we continue popping things off the event queue, executing events, and putting new events back on. So all the way that you interact with different models, the way you create all your models and the timing specifications for those models are with events. So the reason why you always need to inherit from SimObject is that SimObjects are the things that can enqueue and dequeue events. And we'll cover this more after the break. Yeah?
So this queue is always a strict queue, like it is always first in, first out?
It is a priority queue with the time of the event. So event 10 could create a new event at time 11, time 50, time 100. Actually, it could even create a new event at the same time if it wanted to.
So it's basically like the event 10 can create anything that either comes at the same time or just right next. Like it still has the notion.
Yeah, the event queue has the notion of time. So you can create a new event for anything after the current time. You cannot create an event in the past.
Jason,
good question.
Reminder, last questions repeat so that live stream is here.
Yeah, I will do my best to repeat questions. Thanks for the reminder. In fact, anyone can remind me of that. Any other questions? Okay, so what we learned is that gem5 is a cycle level. So we didn't talk about that, but gem5 is a cycle level full system execution-driven simulator. To obtain gem5, you download it via Git or connect via the code space that I gave you. We'll be using code spaces for the tutorial. And next up, we'll be talking about the standard library. So before I turn it over to Bobby, any questions? Okay, great.
Could you go back to the link and the code space stuff?
Yeah.
I'll give you more time to.
There you go. As you can.
Yeah, I'll. Hey, so it's really, really important that anyone who wants to go along with what I'm about to talk about is using, I would much prefer if everyone uses the code spaces. It's going to be a lot easier. So I'm going to give you a minute or so to please go on this link. It should set everything up for you. And then when you get to your repo, you code, and then you click the configure and create code spaces. And you want to go with the 16-core system. And this is all browser-based, so you don't need to download Visual Studio or anything like this. It should just work straight out of the box. And that's what I'm roughly going to be going with throughout this tutorial. If you really want to make your life a little bit more difficult, you can download the repo that this corresponds to and do everything locally, but I wouldn't recommend. So I guess while everyone's setting this up, I'll briefly describe what I'm going to talk about. So what I'm going to talk about is the gem5 standard library. As Jason mentioned, it's something in gem5 that has existed for roughly a year now. It was primarily developed by me, and basically the reason I developed it is I joined the gem5 project about 3 years ago now, and I honestly found gem5 extremely hard to get a grasp of, because if you want to develop even an extraordinarily simple system, you can sometimes have to write hundreds and hundreds of Python, like lines of Python to properly declare your system. And I felt there's a lot of boilerplate, there's a lot of functions that should basically be part of a library which you can use to build systems a lot easier. This is a dirty little secret. I hope no one rats on me to UC Davis, but I don't really know much about computer architecture. So I really wanted to make sure that all of the stuff about connecting up a system in the right way was done as part of a library, and my life can be a lot easier if I want to set up a simple simulation. So I'm going to swap out laptops now. If anyone has trouble with code spaces, flag down someone with a gem5 shirt, and they should be able to help you out. Okay, let's hope this works. Oh my God, it actually worked. It's a miracle. This never happens at conferences. Oh, no, of course. Wait. Of course it didn't work. I think the cable's just a bit flaky.
USB-C then?
I don't have USB-C. That's better. Okay. Future note, the cable is a little bit funny. Okay. Slideshow. Go away. Play from start. Excellent. Okay, so this is going to be my presentation of the Gem5 Standard Library. Just to reintroduce myself, I'm Bobby Bruce. I work at UC Davis. I'm part of the Darker Architectural Research Group, though I primarily do software engineering and work on Gem5 day to day. So, short introduction, what is a standard library for? Well, if you downloaded Gem5 about a year and a half ago, your option was either to take a script someone else had written and use it, or you'd have to literally define every single part of your simulation that you needed to do. Every single connection, every single cache, everything you wanted to define your simulation. And if you want to do any sort of simulation of any meaningful merit, this was hundreds and hundreds of Python, well, hundreds of lines of Python. And we did a survey and asked people how they use Gem5, and the most common response was essentially, oh, in our group, we just pass around the same scripts over and over again, and we modify what we need to do. So this wasn't a very good thing. So we developed a library. Essentially, you can still write Gem5 configuration scripts as you have always done, but now there's a library that does the most common things for you and easier. So when developing this, we had a lot of discussion about how should this work or be conceived by the end user. And we came around to this idea that it should be kind of like, I thought of it as like a computer store or building your own PC, this sort of thing. So as we go through this tutorial, it should become clearer, but the basic outline is, I think, quite simple, that in the Gem5 standard library, you have the concept of a board. And the board can basically have components plugged into it. The three major components are memory system, and that middle one should be processor, and it says cache hierarchy. So memory, processor, and the cache hierarchy setup. So if you want a board with a single channel DDR3, you plug that in. If you want a 3-core CPU, you plug that in. And if you want an L1, L2 cache hierarchy, you plug that into the board. And then you should be able to begin running simulations with that board. Conceptually, it's that easy. Behind the scenes, there's a lot of stuff that's connecting stuff together for you, but that's how the Gem5 standard library works. I'll come back to this later on in the presentation when we actually extend stuff in the standard library, but if anyone's interested in kind of like the class diagram of how this architecture works, this is essentially it. You have an abstract board that boards come from, and the abstract board accepts an abstract processor, an abstract memory system, an abstract cache hierarchy, and some boards accept other exotic components, but this is the basic crux of it. So you can have, you see over here, the x86 board. So if you want to build an x86 system, you take the x86 board, and then you plug in the processor you want, you plug in the memory system, you plug in the cache hierarchy, and you're good to go. And this, so that's essentially the very simple idea much of the Gem5 standard library. So this is so hopefully, I really hope now everyone has code spaces up in front of them. Some sort of interface that looks a bit like Visual Studio Code inside your browser. I want to briefly explain where all this stuff lives inside the gem5 source, because sometimes the best way to find out how stuff works is just to look at the source. So if you go to source, Python, and gem5, that's where the gem5 standard library lives. So this one? No. If you're looking for what all the classic cache hierarchies we have in gem5, you go to gem5, components, cache hierarchies, classic, and here's, at this time where I took the screenshot, that's all the classic cache hierarchies, L1, L2, and then we also have Ruby cache hierarchies. If you want to see all the memory system, oh, yeah, thank you, Jason. If you want to see all the memory systems, you can go to gem5, components, memory, and underneath there is all the memory systems we have in gem5, the gem5 standard library. Same with processors. I won't go into it, but we'll hope to fill out this a bit more in future, but there's also pre-built, which are like pre-built boards to specific configuration targets. And down here at the bottom here, this is mostly just some stuff that we'll go over later, but mostly like functions that are quite useful inside gem5. I'd like to remind people that if anyone has any questions about anything I'm presenting, then please just raise your hand or shout at me a little bit, and I'll try to answer your questions as we go. But yes, this feels like it's dropping in and out. But so that's where you find stuff, and you import stuff in the standard Python way, pretty much. So the kind of key word here is from gem5. So if you want to import a board, it's from gem5 components board, and then the board that you want to import. Don't worry, this will become clearer as we go into examples. I just want to go over kind of how the directory structure works and everything. So here's like a big import dump that you typically have at the beginning of a Python file, and this is how you import stuff from the standard library. And it kind of conforms this directory structure. So gem5 components, memory, single channel, import single channel, DDR3 1600. There, you've got your DDR3 1600 inside your gem5 script there. So I hope you're ready, because we're about to do our first walk along tutorial. So I want you all to start by opening up this file. It should be in front of you. So it should be inside the materials using gem5 02 stdlib and then the hello world file. And you should have all this in front of you already. These 7 lines are just import statements. And what we're going to do over the next few slides is extend this file to eventually create what I call the hello world gem5 program. This is what I would consider to be probably the easiest simulation you can run in gem5 that is in some way meaningful. So I hope everyone sees that in front of them. If not, flag someone down and they can help you. The first thing I'd like to do is type in these 3 lines. And as you're typing this in, I'll talk everyone through them. So the first line here is declaring our cache hierarchy. But for this example, we're just going to say there's no cache hierarchy set up. We're literally just going to say, which basically just means in this, the processor pretty much connects directly to memory. There's no cache hierarchy. There's nothing between processor and memory. It's very straightforward. Then we set up our memory system, which we're saying is a single channel DDR3 1600, and we're saying it's 1 gigabyte. Then we're saying our processor is what we call a simple processor with 1 core, lots of type, CPU type atomic. So I'll give you all a little bit longer to type this all in, but 3 lines. So that's declaring basically the crux of our gem5 simulation.
If you have issues, raise your hand and we can come help.
Yes, please. People on standby, ready to help. I'm totally basing this on seeing when people stop typing, but maybe people are on Twitter or something. I don't know. Is everyone wave your hand frantically in the air if you need a little bit more time? No? Okay. Okay, you guys have got him sorted. I'm gonna move on for everyone else's sake. Don't worry, there's plenty of time to catch up. And the second part is you're almost about to complete your simulation here, amazingly. We're just literally going to add these components you just made to a board. It's called the simple board. So you're going to do board equals simple board. Simple board is a board in the standard library, which is simple. It's straightforward. It doesn't have much in it, but it allows you to connect in these components. The only additional information is frequency. So clock frequency isn't actually that important, but we'll say it's set to 3 gigahertz. And then you set the processor, memory, and the cache hierarchy. That is the CPU frequency. Yeah. Yes?
I mean, the right side of this is just the variable that we have used in the top 3 portion?
Yes. The question was, is the right side of this just the variables you've just declared? Yes, it is. Yes. Do like processor equals processor, you could just do processor, memory, cache hierarchy, if anyone's familiar with Python. But this is kind of our style. We like to make it very clear what's being passed as a parameter. So I think I'm going to move just briefly on to the next slide. Please reach out to a friend if you have any, if you haven't finished this, and copy their work a little bit. Because I'm going to go ever so slightly side tangent, and then we'll come back around to this example. But I want to talk very briefly about gem5 resources. So essentially, what you've got now is almost a full simulated system. Well, a system to simulate, but a system to simulate is pretty pointless without anything to run on it. And that's kind of what gem5 resources are for. I would say my definition of a gem5 resource is something that isn't required to set up a specific it's something that you typically run inside a simulation. So a disk, for instance, a disk image, a kernel, an application. The gem5 resources also provide some cross compilers and some cross compiled binaries. This is provided by the gem5 project, and it's held in our gem5 repository. And the neat thing about the gem5 resources and gem5 standard library is the gem5 standard library has functions that allow you to obtain gem5 resources for your simulation. So I went through that all quite fast, but essentially gem5 resources provide you resources such as disk images and binaries and kernels, etc., for your simulations. Right now, at this exact point in time, we don't have a good web interface to navigate all these resources that we provide. They're just basically dumped in this JSON file. So it's just basically a machine-readable thing. But if anyone wants a quick rundown of what resources we have, you can look at this file. Their name, some very basic descriptions of what it is, such as the architecture, and then some like the MD5 sum and the URL in which they can be obtained. But you don't really need all this information. The only information you really need from this is just the name, just the name of the resource you want to put inside your simulation. So to see this kind of in action, if you go to materials using gem5, standard library, and then this obtaining resources.py file, you should see something, well, you will literally see this. You'll literally see 3 lines of Python. And if you run this command here at the bottom of the screen, this gem5 x86, and then the path to this file, what's going to happen in this script is the gem5 standard library will look up the RISC-V disk image and see if it's available in your current system. And then if it's not currently available, it will download it for you onto your system automatically. And then it will print where that resource exists on your system using that last line there. And if you run this 2 times, the second time it's not going to, the first time it's going to download it. Second time it's not going to download it because it's already available. It's already available in your system. So you can play around with this. This is a way to get things like disk images and kernels and binaries into your script. And you'll see how we're going to do that in a bit. Yes, and so you should already have gem5 x86 available inside your container if you're using the code spaces. And you'll get an output that looks a bit like this. I won't go through this line by line, maybe just the first, only the first. Yeah, well, okay, the first 5 lines are saying that the resource wasn't found locally, and then it's downloading it, and then it's decompressing it, it's putting it where it needs to go, and then if you run it a second time, it just goes, oh, it's like already there, here it is. So that's how you obtain the resources in the standard library. And to go back, oh wait, sorry, one more slide. A lot of people ask, well, what about if you want to use a resource that isn't available inside our resources repo? Well, you can use a custom resource, and a custom resource is just something that you define. And for a custom resource, you would use this API here and specify where the custom resource exists in your system. We're not going to use that in this example, but for anyone who's interested, that's a common question we have when using the gem5 standard library. How do you specify a resource that isn't provided as part of the gem5 community? You just use this. So going back to our Hello World program, we add these 2 lines, right? There's a lot behind the scenes happening in these two lines, but conceptually they're quite straightforward. We're saying, what binary do we want to run in our system? We're saying we want the x86 Hello World 64-bit static binary. Go and get me that. And then you're saying, on this board, set the SE binary workload, which is saying set this particular resource to be run on the board in syscall emulation mode. I still hear some typing, so I'll give a little bit of a minute. So just to go over this again, this will download the resource for you, automatically put it on your system, and it'll set that binary as the workload to be run when you run your simulation on this simulated system. What's the resource? It's literally a Hello World binary. It'll just print Hello World. Yeah, it's just a binary. It's just a compiled binary that will, yeah, that's all. You'll see in a couple more slides this in action. It does exactly what you think it's going to do. Yeah, sure. We've not completed. What you mean the? Well, the. I'll get one of my tech support people to come and help you.
Run it with gem5. So gem5 is a Python.
Oh, are you trying to just run the? Oh, are you just trying to run the Python script directly? Oh, I see. Yes. So gem5. So basics of gem5. Gem5 itself is a Python interpreter. So you want to we will get to this, but you want to run this script with gem5, okay? Gem5 will parse the script for you and resolve all this. Okay, thank you for that.
Yeah, you can just use gem5x86.
Yeah,
it's in bin. You don't have to. You don't have to compile it.
Yeah. So, and these are the last. These are the last 2 lines that we're going to add to this script, and this is just this using the simulator module. I'm going to go back and talk about simulator module in more detail later on in this presentation. But simulator module basically ties everything together. It takes in the board that you want to simulate. At the moment you hit line 28 here, your simulation starts to run. Okay, so the simulator equals simulator, and then you declare which board you want to simulate. In this case, the simple board that you created. There, don't run. I'll give it one of it. And yes? So the question was, can you just provide just like the CPU? Right now, the gem5 standard library is very board-centric, so you would have to pass a board. But it would be possible to create a board that is so basic, all it is a board with a CPU plugged in it. And you can simulate from there. We don't provide anything like that, but it's definitely possible. Yeah, but no, for this particular API, you're passing something that has to inherited from abstract board. And I just want to make so this is the entirety of what should roughly be in front of you, roughly like 25 lines of Python. So I would consider probably this is getting very close to the most basic program or thing you can simulate inside gem5 with the standard library. And then to run this, you would use gem5 x86 and then the path to that file. So just like a disclaimer, if you're using code spaces, you shouldn't need to compile gem5 because we already have some binaries there for you to use. And then when you execute this here, you're going to execute your script and you're going to run your hello world simulation. And if you work with gem5, you'll be used to this. It likes to dump a lot of warnings and little things like that to your terminal. But the real thing you're interested in here is at the end, it says hello world. You've executed the binary inside your simulated system, and the simulation exits. Now is a good time to ask any questions about what we just built. Because I went through quite a lot. But if I'm happy if my teaching is so clear. This is all very intuitive. Oh yes, hello. Yeah. I'm not going to cover how to do traces in this presentation. That's a bit more of a topic. But in the next slides, I will cover how to look at the stats, outputs, and things like this. Yes. Good question. I just only got an hour and a half, so I wanted to make very high level things. Okay, I don't know why. I don't think I should. Okay, I thought I had a more detailed slide here. But if you go, so I thought I had pictures here, but they haven't appeared to come up in the version of the presentation. If you go to the M5 out directory, in gem5, M5 out, you'll basically see kind of two things. A lot of files that are config.something and stats.txt. And the config.something is just literally a definition of your configuration in various formats. If you want the most human readable one, that'll be config.ini. And that's all that is. And if you want the stats output of gem5, that is stat. You can go to stats.txt in the m5 out directory, and those will give you various often for any simulation that is of any reasonable length. A ton are reported by various components inside your simulated system. At the top of that file, there'll be things like simulated time, number of tests, number of instructions simulated, and things like this that can be useful for things. So I suppose now is a good time to kind of, you could play around with even this very basic design and see like how clock frequency impacts like the simulated execution time, things like this. So that, and I suppose it's also worthy of note that the M5 output, more complex simulations will have other data. So if you're running a full system simulation, you will typically get the terminal output of the simulated system. So if you're booting like a Linux kernel inside a simulated system, the M5 will contain the terminal output of that boot as well. But for this, obviously, this very borderline bare metal simulation, there's nothing really much else out in the M5 out directory. So, a design, how do we like extend it? So I just want to go back and remind you that like we made gem5 as modular, and we made the standard library to be equally as modular. In fact, even more so. So in general, you can replace components with other components inside the standard library, and as long as they're of the same type, you're good to go. So for those of you who can remember back to when you learned about object-oriented design in college, or maybe you still work with it, this is an object-oriented design. So anything that accepts an abstract processor can accept any type of abstract processor, and it should work in most cases. So let's add a real cache to our design. Like, how would you do that? And this is basically all you'd need to do. You would need to import the cache that you want. So in this example, how about you go with a private L1 cache hierarchy, and then you literally replace, in this case, just one line. You'd replace line with this line here. So you'd say your cache hierarchy should be the private L1 cache hierarchy with these data and instruction cache sizes. And then I'll give you time to type this up and put it in. Some of these imports can be very long, so make sure you get them right. But literally, the takeaway I want you to do here is to literally see how your design functions with quite actually a significant change. You added a whole cache hierarchy setup here to this design. It requires you to modify 2 lines in your Python, or add 2 lines. And then when you're done that, you can rerun the simulation and see it working. And eagle-eyed among you can look into the stats and see how the stats change. Because obviously with a cache hierarchy setup inside your design, it's going to run faster, more efficiently. Is everyone happy? Yeah? Okay. So, okay, I've been told to give everyone 2 or 3 minutes. We are about to move on to a different example. So this is concluding the Hello World example. So I guess now good for me to run down like what you should have learned so far. Should have learned that at the center of every when you use the gem5 standard library to build a simulation, at the center of your design is the board, which accepts processor, cache hierarchy, memory system. You can plug these in a modular way to get the system that you want. Then you do simulator with the board, simulator run, and in almost all simulations, you're going to require some sort of binary or disk image or something like that. So you can get these using the gem5 resources, and we provide increasingly every single version of gem5. We're providing more and more. So, and we're going to show in the next example using more complex resources such as kernels and disk images. Yeah.
Can you also give a list of files that you should have looked at, like stats.txt?
Oh, well, yes. Also, we went over the stats output. Well, briefly, there's a lot to talk about in stats I won't get into in this presentation, but if you want to know where the stats live, you'll look to the m5 out directory and stats.txt. If you want to ask me afterwards, there's a way to output the stats in a JSON format, which I personally prefer, but the stats.txt is definitely the most human readable. Anyone got any questions or? Oh, hello?
I think I can probably find it myself. This is a private L1 cache, so that means there will be like shared L2, L3.
Okay, first of all, completely possible to make one. I can't remember exactly what we provide right now. I think we provide a private L1 and then we have a private L1 and private L2 cache. I think there might be, and there's a few more what we call Ruby caches, which are caches I won't go too deep into that right now. We're hoping to expand these to provide more in the future, but yes.
Yeah, I think that's a really good point. Let us know what you want. Yeah, I think right now we just have a simple like single level cache and a simple private 2-level. Clearly, we need things that are more realistic, but we're open to ideas. Anything is possible. We just haven't written the code for everything. Right?
I kind of see it as this. We've kind of built the infrastructure and the roads for all our components, but we haven't built a lot of components. So, but yeah, if we have time at the end of this presentation, I'm going to show how you would create your own cache hierarchy in gem5, in the gem5 standard library. And then once you've done that, you can just, let's say, push your contribution to gem5. Yep, question here? I'm sorry, you're just really far back. Ayaz, what was the question? Oh. So, moving from classical to what? You mean moving from an old version of an old way of doing it to the standard library?
No, also
yeah.
From the classical object, for example, you type atomics, and going from the classical CPU notation, you build a notation with rotating from the classical object. How to pass the gem5 board, where a form or the form.
Okay, so sorry, I just had I think I got every second word of that. So I'll just move right next to you. What exactly is your question? Oh, well, that's helpful. Okay.
How much work does it require when you go from doing classical SimObject like a CPU or like how you implemented it originally in gem5 and passing it to the standard library and using it inside your standard library implementation?
Okay. So yeah, so I'm going to stop using this because this keeps dropping in and out, and it's more distracting than it's worth. But the question was, I think the gist of your answer is, question is, how do you go from developing a SimObject and incorporating it into the standard library like this? So essentially, it's kind of up to you. As long if you remember the class hierarchy diagram at the beginning of this presentation, as long as your component conforms to the interfaces, you're kind of good to go. So the common way to do it would be you take your SimObject and essentially wrap it inside an interface that conforms to the like, interface of that superclass, and then you can plug it in. And that's commonly how we do it. Typically, things like, for instance, we have the processor, the abstract processor. That's actually multiple SimObjects, because in Gem5, the kind of SimObject is a processing core. So a processor will have many cores, for example. So yeah, it's essentially, it's up to you. You can simulate things however you want, but typically you would wrap the SimObject or SimObjects you need inside standard. I'm sorry, I had trouble hearing you over the back. Well, I might stop using this, but well, I'll get someone to relay questions from the back. Does anyone have any other questions before we move on to a slightly more complex example that should incorporate that? Okay, everyone's fine moving on to the scary stuff? Okay. So what I want to show you now, I've showed you Hello World. I want to almost leapfrog into something that actually looks like a real computer system. So by the end of this, I want you to have an x86, what I would say a full system, and this system is going to boot Linux all the way up to user space, load a kernel and a disk image appropriately. And I want, even though I'm going to introduce some new concepts here, I also want you to realize that by the end, it's actually quite simple and conforms to a lot of the same ideas that we introduced in the first half here. So first of all, I want you to navigate to this file here. It's in the same directory as before. It should be called x86 fullsystem.py. And there, I've just given you all the imports you need to save your wrists all the typing. So if you go to that file there, you should see 11 or so lines of Python already there for you. So first thing I want you to do here is add these lines here. And this is actually an optional step. You don't need to put this into your design, but this is something we found really helpful. The standard library has this requires function, which essentially, when you're running your simulation, your Gem5 binary has the properties. So in this case, we want the ISA required to be x86. So the Gem5 binary you're running has to have the x86 ISA compiled in. It to have this cache coherence protocol compiled in as well, messy 2 level. So right now, like, literally, kind of incorporate the multiple cache coherency protocol targets. But right now, it's typically that a binary will normally have one of each. It'll have, you have an x86 messy 2 level Gem5 binary. So the basic takeaway of this is we just want to run some checks before we dump in and start simulating code. This will give us a helpful error early on inside our Gem5 simulation. Okay, I'll move on to the next slide. So these lines should look pretty familiar to you, but we're just adding slightly more complex components. So we're adding a cache hierarchy again, but this time we're adding a messy 2 level cache hierarchy. And we've got more things we need to declare, such as, well, more cache sizes to declare, the number of L2 banks, and everything else there. I would just go with these sensible defaults I have on the board. If you really want, you can change the size of the caches and see how your simulation performs. But I typically go with these values just because they kind of make sense. And then for memory, just do the same thing as before, single channel DDR3 1600. You can probably set that to, yeah, 2 gigabytes is fine. I'll give you a minute to type this up. I hope this is kind of intuitive and clear given what you learned in the first half here. Yeah.
I don't feel like you have 10 to 10. Don't rush.
I thought I had until 10:30.
Okay.
Okay, great. I thought I was making really good time there when I thought I was going to finish at 10:30. Okay.
Officially it said 10. I was looking for it. It
Okay.
was 15 minutes behind.
Okay. Yeah. I was thinking teaching this will either take longer than I think or shorter than I think, but it won't take as long as I think, for sure. Okay, sure, go ahead.
I think earlier and here as well in the L2 size, we're giving it 256 kilobytes, right?
Yeah.
And in the L1 instruction of data cache, we're giving it kibibytes, I think, with KI.
I forget, Jason, does gem5 respect these kibibyte and kilobyte definitions?
If all memory sizes, you should repeat my answer. All memory sizes are powers 2. We're
Okay.
trying to make sure to use KI instead of K, but I would call line 26 a typo.
Yes. So good answer. That line 26 should be kilobytes. There should be all memory sizes in Gem5 are powers of 2. But I believe, well, this I know for a fact this still works, so it's fine. Yeah. Okay, I will move on. I think that's safe. Okay, no one's screaming in agony at that thought, so I will move on. So this is a little bit more of an exotic component in Gem5. So I'm going to spend a little bit talking about it. So in Gem5, you don't always really want to be running exactly the same system for the entirety of your simulation. And a good example of that is what type of core model do you want to use? Do you want to use a core model that, in short, is precise or not so precise? And where that comes in handy is, so where you'd want to switch up your simulation a bit is if you've got a really big workload to simulate, but you only really care about getting good quality stats for a very, very small region of interest inside that simulation. So for example, a very common thing that we do in our lab is we want to say, run an application in the Parsec benchmark suite, right? But to run the Parsec benchmark suite, you need literally to boot the entirety of the operating system up to that point prior to actually running the application. So you don't really care about the simulation stats for booting the entirety of the operating system. You want the stats for just the running of that application inside the OS. So in that case, you would boot the simulation with a low fidelity CPU of some kind. And then when your application starts, you swap out the cores and then simulate with the cores that give a high fidelity statistics. That's essentially the gist of it. So if you actually look at scripts of Gem5 scripts people use in the wild, they typically use this strategy of stop your simulation, swap out the cores, and now we're going to simulate with something that is a little bit more precise. So this is why we developed the simple switchable processor. And given my explanation, I hope it's a bit clearer now. You start on some kind of CPU type, and then at a point in the simulation, you can call processor.switch, and it'll swap to the second type. So this is a reasonably okay example because like O3 CPU is an out of order CPU model, and it takes like forever to run anything. It's because simulating that sort of component is very costly. So in this strategy here, we're starting with a much more simple CPU model and then switching to the out of order model. And we're saying the number of cores will be 2. And the only reason I did this is just show you that, we did 1 core before, but if you just want to use multiple cores, you literally just up the core count here. And behind the scenes, gem5 will stitch everything together for you. Yeah, and there's a small text just basically reiterating what I said. So yes, we're going to use the simple switchable processor here. Is there any questions on that?
And the reason why you do it is to make it fast, or to you start from like a complex processor with a loading operating system, and you just have you switch to 64.
Yeah.
Just to run your application.
Yeah.
That's the only reason you make it faster.
I can't think of any other reason apart from how long the simulation takes. You're free to do it for other reasons. That's the only reason I can think of. You really just want to get to the point in your program you want to simulate fast before switching to something that's more detailed. Yeah, it's a simulation is very, very costly. It takes forever to run to simulate. You can often just take any tricks you want to get. So moving on to the next slide. This should be extremely familiar to you. The only difference between this and your first program you've written is we're using the x86 board because we want to use an x86, a board that supports an x86 full system simulation. So type this up as before. I hope this is clear. You want to go? So I'm going to go back to the previous slide just because someone requested that. Oh, sorry, question at the back?
Yes. I just want to ask a question about switching.
Yeah.
Is it possible to switch back and forth, or is it just one time switch and that's it?
Okay, so the question was, it's possible to switch back and forth. My conservative response to this is, in theory, yes. Though I've done this a few times and just had the simulation completely crash on me. So, normally you'd only really want to do this. Well, yeah, but there's circumstances where you'd want to flip back and forth. Complex maneuver behind the scenes for gem5 to do this, but yes. I suppose I might as well just highlight this here for the thing. On some systems, unfortunately not the code space systems you're currently running on, you can run in KVM, which essentially just allows you to run the gem5 simulation on your host CPU. And that's as fast as your host CPU. And in that case, you would do starting core CPU type.kvm, and then you'd switch. So you basically just essentially run the simulation on your host system up to that point, and then you switch to a simulated core. I'd really like to demonstrate that, but it requires a virtualization that isn't enabled on code spaces. And actually, it's not even enabled on all hardware in general. But I believe there's a post on the website that outlines how you can check if your system has this enabled and how you can run it. But yes, so this is all about just making things faster. And I hope everyone's basically got this. If not, you can essentially, you can copy and paste from your previous example, and the only thing different is the board. It's not simple board, it's x86 board. Okay, this I'm going to spend a little bit of time on because it looks, so it's a slightly more extended version of what we did before with the gem5 resources. So here, skip out the first command here for a second and go to line 25 and 26. We have two resources. The first is the kernel that we want to run, and the second is the disk image. So this is an incredibly common setup for running a full system simulation, because modern systems have kernels and then they boot to, yes? So I'm about to go on to talk about M5 exit instructions. So just let me explain the resources first, and then I'll jump back up to that M5 exit thing soon. So yes, for like real world systems, this is the typical setup. So this is a very common function you'll use in Gem5 standard library. It's board.set kernel workload. So that's going to declare to your configuration that we are going to run a full system workload that is going to boot a kernel. And then from there, somewhere down the line, use that disk image that we provide. What's interesting about this workload is we can set the read file contents. Do I have another slide here? Or... Oh yeah, I do. Cool. So actually, I'll talk about this in a little bit more detail soon. But essentially, this read file contents allows you to set a command to run once your system is booted. So once our system is fully booted, we're going to run M5 exit. Right? What does M5 exit do? M5 exit exits your simulation back to your Python script. So you can do simulator.run, and it'll run up to that first M5 exit command. We'll turn to the Python script. And from there, we can do processor.switch to switch our processor out to the more detailed processor. Run simulator.run again, which will run, in this case, echo. This is running on the timing CPU cores, which I don't think is true, actually. It's going to be running on the 03 CPU cores. Reminder to yourself to update this slide. It's going to sleep for 1 second of simulated time, and M5 exit again, which will exit the simulation for the last time. Don't worry if you struggled a bit understanding that. I'm going to go over this a bit more again. I thought this was helpful, but maybe not exactly. But this is essentially, so you'll notice here that we're setting read file. You know what, I'll go back to this slide because I don't expect you to have this all typed up right now, but I'll talk briefly about how this all fits together. Notice it says read file contents. Well, read file content, there's a gem5 command that essentially will read. This will, it's a gem5 instruction that you can put inside a workload that when executed will read whatever you set there. So inside this disk image, we have this script here. And basically, the TLDR of this is if you have set something to read, it tries to execute it. So we have set something to read. We have set this command to read. And when this disk image is loaded, it tries to run it. I don't think this is super important. All it really is the way we set up this disk image is to run a command that's passed to it. OK, so I'll just give everyone time to type this up because we're going to go on to how this executes. But while you're all typing up, I'll explain again how this works, because this is going to be important to understand when we start to develop more of this simulation. What we're declaring here is a simulation to boot. And then once the OS is completely booted, it's going to immediately exit the simulation, which allows us to do things like reconfigure our system slightly. And then we can run the simulation again. It will start off at line 20, you can see. Basically, when it exited before, it's going to return to that point in the simulation. Going to run whatever we specify here and exit for a final time. So simulator module. This is where the simulator module starts to become a bit more complex. And I want to kind of put this disclaimer here. The simulator module is currently kind of in beta status. I don't want to promise all these APIs are going to remain consistent across Gem5 versions. That's just a disclaimer. But I will explain how it currently works. So simulator module will look out for what we call exit events. Exit events are when your simulation ends for some reason. So having an M5 exit command is an exit event. And there's 2 in the simulation. And the simulator module allows you to handle what you do at these exit events. So you could do nothing, but it exits and you can declare what you want to do. So I'm going to say you don't need to type this up because we're going to implement something better. But this is like an idea of what you could do in this program. You could do simulator equals board as you did before. You could run the simulation. That's going to run the simulation up to the first M5 exit event. And here we can do things between the exit events, or between the first exit event and when you run again. And here's a good time to switch our processor out, right? To move over to the more detailed simulation. I wouldn't bother typing this up because I'm going to show you a better way to do it, just in one more slide. But does everyone kind of understand how this works? The simulator will handle the exit event for you. You'll exit, and you'll be able to do something, and then run again. OK. But I think we can do a bit better, and this is what I want you to type up. It looks a bit more foreboding, but it's actually a much better engineered way to exit your simulation. So the simulator allows you to say, on exit event, what do you want me to do? And there's different types of exit event, because different reasons your simulation can exit. I won't go over all these, but maybe my top few. Exit event exit, which is when you run the M5 exit command. Exit event max tick, when you've declared that the simulation should only run up to a certain amount of simulation ticks. That's another exit event. Exit event user interrupt. If someone types Control-C, that's another sort of exit event. So the simulator will catch what type of exit event it was, and you'll be able to declare what to do when you reach that exit event. So in this one, we're saying, and we use Python generators for this. So on this example here, we're saying, on the first exit event, run processor.switch. And you notice there's only one item in this generator, so it's saying, only do this for the first M5 exit event. The second one, just run normally. So this is using Python generators here. And a generator, for anyone who doesn't know, is essentially that thing inside the brackets here. It allows you to, can't think of a good brief one-sentence definition of what a generator is. It allows you to iterate through a list of items. So in this, we're saying exit event. For an exit type exit event, the first thing you should do is switch processor. And for the second one, just return to default behavior and exit. So this is quite useful because if you wanted to do something like you wanted something to happen in the first exit type exit event, maybe we should come up with a better name for that, but an exit type exit event, but you also want something to happen if the user interrupted, you can declare that here. So you could do exit event dot user interrupt and create a generator that, I don't know, maybe it just complains. Maybe it dumps the stats output. Maybe it does whatever you want. Or maybe that's when you decide to swap the processor. Maybe you want to swap the processor exactly when you do Control-C. So this is quite powerful. You can do it this way if you want. There's no stopping you. And this is very easy to read. But it doesn't allow the same amount of flexibility as using the kind of generators and declaring what you do when. So I would just type this up, and I'll give you another minute. Does anyone have any questions on this? Because this is quite, I think this is a little bit more conceptually complex than other things. Does everyone fully understand what we mean by when I say exit the simulation? Because you're not you exit the simulation back to like the Python script level. Yeah. Are you asking? Did you say? Do you have to implement the checkpoint yourself? Yeah, okay. Yes, that's a good question. You have to declare these yourselves. So, obviously here it's pretty intuitive. We put them in the script, right? The M5 exit. There's other ways to do it. You can. There's a Python. No, sorry, not Python. There's a C library that you can import into a C program that allows you to run these sorts of exit events inside a C program. There's some other exotic ways to do it, but I think those two are the most clear ways to do it. You can either do it via scripts or compiled into a program. But yes, you have to declare these yourselves inside your workloads. The gem5 resources have these inside them already. But if you're making them, if you're making your own workloads, you would have to add these yourself.
What's the default exit? What's the default implementation for the checkpoint exit?
Oh, okay, that's a good point. These exits do have default behavior.
Does the checkpoint actually check it?
No. So sorry. Yeah, I understand the question now. Does checkpoint actually checkpoint? Okay, I think the answer to that question is no. But it's also important to know these have default behaviors. So which you can override, but they do have default behaviors. So I probably the one that is most easy for everyone here to understand because we just went over it. Exit event switch CPU will switch your CPU for you, right? I just didn't want to put this in this example because then we wouldn't have to run processor.switch and then it's kind of pointless. I believe work begin and work end. Those are normally used to declare your regions of interest inside your program. So I believe when the work begins, your stats are wiped, so you can get your stats from a clean. And work end, dump the stats to M5 out. Yeah?
In matchstick or user interrupt, you exit the simulator. But when you call the simulator again,
Yeah.
it doesn't start from the state at which you exit. It's the state bypass.
No, I think it should start from the state that you exit.
Switch CPU, the understanding is that when you exit when you do an exit event, and then when you do an exit event switch CPU, and you do a switch processor,
Yeah.
then one expects the simulation to restart from the same old reserved state, right?
It will restart your simulation from the point that you exited.
Yeah.
Yeah.
It will maintain the state and then continue from there.
Yeah.
I think the question at the back was, and that's my question, that similarly, exit events other than the switch CPU will also start from the old state, or which of these will start from the old state?
If you start the simulation again, it'll start from the old state. I believe that's true in all cases. I think that statement's true. Definitely for all of them, yes. All of them listed here. Okay, so I'm not going to ask. You can maybe start running this if you want and exit it, but because it's a full system simulation, it's going to take forever to actually complete. But if you want to run this, you should just to see it do the first few cycles of the thing. You would do gem5 x86 and then up to this Python. And that would run, if you give this enough time, that would run all the way up to boot. M5 exit event triggered. You switch your CPUs. You go back in. You run your echo statement and your sleep statement. simulation ends for good. If you go to the M5 out directory, you will see the terminal output of that simulated system. So you'll see your echo statement, which is pretty cool. So in this last part where we're running the full system simulation, I've introduced the how you declare your requirements at the beginning of a simulation. We've incorporated a more exotic Ruby cache hierarchy, the MESI2 level cache hierarchy, and you saw how that's the same as before. Introduced the simple switchable processor, which allows you to switch processors. And I've showed you how the simulator module can be used to manage a simulation exit event. Does anyone have any questions about all that stuff we just learned? Because that's a lot of stuff in a very short period of time. But there's no necessity for a require function. The reason I implement that in the library is if you don't have that and you've not got the right gem5 binary, the errors you can get can be rather strange and unintuitive. It'll just complain about having a missing import or something. And that's why I find it good to declare at the beginning of your script using the requires function, because then you'll get an error that literally says, I expect an x86 binary and I've not got one. Yeah.
You mentioned the ARM CPU and the x86 CPUs.
Yeah.
Others like this?
We currently support to varying levels, but the main three ones that we support quite well are ARM, x86, and RISC-V. We also support MIPS, Power, and Spark. Yes. Yes, RISC-V is increasingly getting more and more support. We're currently in the process of trying to add vector extension support. Yeah, future's pretty bright for RISC-V in Gem 5.
But I'm from IBM, so will you be covering anything about how one adds a new CPU support or some workstation?
Sorry, what support?
Add how someone contributes or adds to a new CPU support. Includes a new CPU module.
It's a separate. I'm not sure I fully understand the question. You're asking if we're going to add new CPU models?
Yes.
Do you mean CPU models or new ISA targets? Because in Gem 5, there's a distinction between a CPU model, which would be like an out-of-order model or a timing model, and the actual instruction set architecture. Both. I don't think there's any plan. Like, it's an open source project. Anyone can push anything anytime. I don't know anyone who's looking to add new ISAs, whatever they may be. It seems like a lot of focus now is on RISC-V, ARM, and x86, and then we support the MIPS, Spark, and Power, mostly for legacy reasons. We would like to get better CPU models going forward. A common complaint is our out-of-order CPU is not representative of much that's been developed this side of the 21st century. So we're trying to create better models for sure. Anyone got any other questions, or was that? Oh, sure. Sure. So right at this exact moment, which is purely that I haven't got around to extending the library to do this, but I almost certainly will for the next release of Gem 5, because it's been a common request, is you can't specify the number of instructions to simulate to. You can't request a number of simulation ticks to simulate to. So there's actually a parameter inside the simulator, which is like max ticks or 2 tick or something, one of those two. And you will specify the tick you want to exit the simulation at and go from there. But definitely in the next release, I'm going to be working on people commonly say, I don't care about ticks, I care about the number of instructions executed, which is fair because ticks is just a meaningless simulator term. So yes, there's no conceptual reason that shouldn't be there. I just haven't got around to implementing it. I can't remember exactly how you do it, but there's scripts floating around that do something like this inside Gem5. I'm just not the person who wrote them. So yeah. Okay. Anyone got any other questions? Yes?
In terms of the simulation, is there any plan to support parallel simulation? Not simulating a parallel modifier, but run the simulation.
Okay, that's a great question. People have tried and failed to make Gem5 multiprocessor. I'm sorry, like a multi-threaded application. So I've got no. I've seen people try to do it and fail, so I don't want to try myself. But I've always made the case that 99% of the time you're wanting to run multiple simulations anyway, and you can run Gem5 in parallel with other Gem5 instances. In that case, that's a way to get more bang for your buck. But a single run of Gem5, we've got no plans to make that multi-threaded soon. Yeah. It was built single-threaded, and it's really quite hard to change right now. Anyone got any other questions? Great. I will move on. Do we still have time, Jason? Oh, there's a question, sorry. Maya, can you just relay the question? Just I need an amplification. What was the question, Maya? Okay, sorry. I just really struggled to hear from right at the back there.
And the real issue is when event 2 iterated, because Gem5 is not suited for this way. It's quite for the user free or other type of render errors. But if you run one notation different event 2 that doesn't iterate, they are supposed to do quite any. So the real issue is that some SimObject have static iteration position, but in theory, Gem5 is already able to run this way, just not a single simulation. It's really so.
Okay, I've not seen this being tried, but okay, yeah. 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 Okay. Cool. Thanks for the extended an extension to my answer. Thank you. Anyone got any other questions? I'm about to move on to how we can essentially add our own components to the library, which. Oh, okay, I'll move on. Yeah, I'll go over this quite fast. So, if you remember this design, this is what I showed at the beginning of the presentation, and this is essentially the class hierarchy thing. And if you really want to zone out for the rest of my presentation, here's the takeaway. If you want to add your own components to the Gem5 library, you literally extend one of the abstract classes that is relevant to you. So if you want to add your own memory system to the Gem5 standard library, you write your Python script and extend the abstract memory system. And then there'll be abstract classes inside that need to be implemented. And then you'll implement them. And then you can use that component as if it was any other component inside gem5. So I think I'm really going to go quite fast through this because I was going to have you do a lot of writing, but maybe this is something you can maybe do in your own time. But if you open up materials using gem5 and then 02 sclib and then this cache hierarchy file here, this is an example of creating your own cache hierarchy in gem5. Your own classic cache hierarchy in gem5. And the key line here, I think, is line 7, where you're just declaring the class and you're saying it inherits from abstract classic cache hierarchy. And then there, if you look into the abstract cache hierarchy class, you'll see there are 4 abstract methods that need implemented for this to work. So, well, no, sorry, there's 3. You obviously have to declare the constructor, but then you've got the get mem side port, the get CPU side port, and then the incorporate cache into the board, which is the more complex function here. Yeah, in the interest of time, you don't have to go along with me. I'm going to go through these slides. There is a completed version of this inside the stdlib/complete or completed. There should be a directory there that has a completed version of this. So what you do if you want to create your own cache hierarchy setup is you'd first of all implement the functions. So in this case, you'd implement the mem side port and the CPU port, and you'd implement the constructor. So here, the constructor constructs and creates a mem bus with a 64-bit width. And it uses the mem bus as the CPU side port and the mem side port. And then you'd, in this case, this example is going to get you to create an I/O cache. But I hope you understand here, you create the I/O cache into the cache hierarchy. And then you create your incorporate cache. And you can do whatever you like here, but essentially you look up the board and you interact with the board to set up the cache hierarchy. So in these lines here, we are creating all the caches we need. We're creating one data and instruction cache per core inside the board's processor, and we're creating MMU cache for each core as well as two MMU caches for each core as well, and then we just connect these up. The code's here is quite complex, but this is all necessary. So we're saying for each core, you need to create, you need to connect that core's connect iCache and connect dcache, and then you need to go through and set the mem side and the CPU side for each cache as well. Set your walk reports thing. But the punchline is, once you implement all these functions, and there's already cache hierarchies inside the gem5 standard library you can look at for inspiration. Once you've done that, you can just import it like you'd import any other Python module. And as long as the code's in gem5's Python search path, you can import it. And I get a little hint here that if you ever want to extend gem5's path, you can just do import sys and sys.path append and add that as well. And I was going to have a little homework for you, like, well, why don't you create your own cache hierarchy and try to incorporate it into your Hello World program and see how that works. That's essentially how you do it. I have totally steamrolled through that at like 100 miles per hour in the interest of time. But does everyone kind of see the core thing as you extend the abstract classes and you implement the abstract methods? Yep, that's how you do it. And if you get confused, it's open source. Go into the standard library source, and you can see other instances where we've done this. So you can look into the private L1 cache hierarchy and see how we implemented that, i.e. how we implemented those abstract methods and then incorporated it into gem5, created that component. That is my last slide. Does anyone have any questions about, I suppose, anything I've taught in the last hour and a half? Anyone have any questions about Gem5 or comments or anything? Floor is open. No, wonderful. I'm going to take silence as everyone's very happy. Reminder, there's a Gem5 workshop this afternoon where we're going to, various people are going to present their research and stuff related to Gem5. Hope to also find some time to have some more meaningful discussion about the future direction of Gem5. And if not, it's a great networking event for people who use this tool or simulation tools in general. So, please attend. I'm going to hand back to Jason, who's going to go over some other materials. Oh, thank you. Oh, do you want?
All right, so there's a coffee break in like 5 minutes or something. We'll give you 5 extra minutes of break time. Then we will be back here at 11. And I will go over how to make a new model in Gem5 if you want to extend it to model your new great idea. And then also talk some about like some of the ISAs and CPU model things came up, a few questions. We'll also talk about generally all the kinds of models that Gem5 provides and some other Gem5 features. So see you all back here in 30-ish minutes at 11.
What's the lunch break again?
Noon. I'll say something about it in a minute.
This walk during lunch, this afternoon lunch, we were wondering through trying to figure out what we want to do to eat.
I don't know.
Okay.
Kind of up to y'all. I'm okay with winging it.
Okay. Okay. Well, I guess we'll figure out then. Okay.
Yeah. Sorry.
Have you been there the whole time, Melissa? Have you been here the whole time? Yes. Oh, I didn't notice you. Oh. Nice to meet you.
Okay. So we're going to do a lot of coding together this time. So get ready for that. Hopefully we'll be able to read my screen. It's smaller than I would have hoped for, but we'll get through. Am I connected? Is the mic to the camera working? As long as all the lights are on, I think I'm good. Okay, then I think I'm good. Oh, okay. And the camera's on? Okay, great. Okay. Any questions or anything before I get started? Okay. Well, we lost some people at coffee, but maybe it'll come trickling back in. Okay, so in this part, we're going to talk about how to add your own models to gem5. So Bobby talked some about using the standard library, which is the way we're encouraging people to, this is the interface we're encouraging people to use to take the models that are in gem5, configure a system, and run the simulation. But now we're going to talk about how to create those models in gem5. I'm going to go over a couple of examples of creating some very simple models. So these models aren't going to be particularly interesting. They're not going to really do anything, but it'll give you an idea of the APIs that you might need to use when you're creating your own models from scratch. Okay, so before we dive into anything, I want to have everybody bring up their code spaces. And we're going to start building gem5 because it's going to take 10 or 15 minutes to build gem5. Oh, I guess one other thing I'll mention is, so we're a little bit behind what the schedule that I would have liked to have been. But it sounds like the conference is not providing lunch. So I think I'm going to take that opportunity and force you to stick around for a few extra minutes and just steal some time from your lunch break. Sorry. My prerogative. Okay, so we talked briefly about what you need to do to build gem5 when I first talked about it. We're going to use scons as our build system. So this is in the gem5 directory. We're going to use scons, build. I'm going to build the null ISA, which is, so we're going to create a gem5 binary that doesn't have any ISA built into it. So we're not going to be able to execute code with this, but we will be able to use it as a simulation framework, which is what I'm going to be showing as an example. And then importantly, we need to build this in parallel. Otherwise, we'll be here all day. I hope all of you have chose the 16 core environment when making your code space. If you didn't, you can use Control-Shift-P, type code space, and there's an option to change machine type. It takes a few minutes, but you can change the machine type to something else. So my current machine type is a 16 core, but you could switch yours if you need to. So since we have 16 cores, I'm going to use 17 threads to build gem5. And as I said, this is going to take about 10 minutes or so. The fewer cores you use, the more time it's going to take. And it also requires like 8 gigabytes of RAM. So if you have less than 8 gigabytes of RAM, it just isn't going to work. Through some stuff. Anybody need me to talk more about building gem5? Scons, build null gem5.opt minus J17. Let me, here, it's scons, build null gem5.opt minus J17. Null is we're going to build a binary without any ISA support. So it's not going to support x86 or ARM or RISC-V. Just no ISA support. It takes a little bit less time. You can't run any binaries in it, but you can use it for simulation, for simulating. We can use the simulation framework part of it. Yeah.
Did you change from gem5 tutorial to bootcamp environment?
I switched into the gem5 directory. So I did CD first. Yeah, sorry. Okay, great. It seems like some percentage of the room figured that out. So if you have a question, ask the person sitting next to you. Okay, before I dive into this, I want to briefly talk about gem5's coding guidelines. So we have a pretty strict style code for contributing to gem5. And I strongly suggest you follow this even if you're not planning on contributing. It's a good idea to have a style. So one of the first things it's going to do when you run scons is ask, do you want to install the style, the hooks for the style guide? Click enter for yes. And don't ignore the style warnings and stuff. Trust me, it makes things a lot easier. We'll see this in a minute, actually. I'd also suggest using Git branches and things for your features. I don't think I will here, but when you're developing something, create a branch so it's easier to keep track of things and potentially update gem5 in the future. Okay, so let's go through adding a new model, adding a new SimObject. So 5 steps to do this. First, we're going to declare the SimObject that we're going to create. Then we're going to implement that SimObject in C++. Then we're going to register the SimObject so it's built with gem5's build system, rebuild gem5, and then we're going to create a configuration script or a run script that actually uses that new model. All right, so let's dive into this. So I'm going to create a new directory in gem5 called tutorial and work out of that. So in this tutorial directory, I'm going to create 4 files. I'm going to create my SimObject.py. So this Python file is where we're going to declare a SimObject. I'm going to create a my SimObject.cc, a my SimObject.hh, and oops, that was a directory. And finally, I'm going to create a scon script file, which is what we're going to use to make sure we build everything. Yeah.
say again where people should create these files?
I'm creating, oh, sorry. I created it in the wrong place. This should be inside the source directory. So in gem5 source tutorial is where I'm creating this. Sorry about that. So the full path is gem5 source tutorial. I can make it a little bit bigger. I can't make it too much bigger, unfortunately. I think this is about the best I can do. By the way, if you can't read this or you want to copy paste, if you look in materials, developing gem5 models, 02 SimObject, all of these will be in the complete directory down there. Okay, so first step I said was to declare the SimObject in my SimpleObject.py. So I'll briefly mention here, part of our style is SimObjects are camel case without underscores, whereas the C++ files that contain the implementation are snake case, all lowercase. So in my SimpleObject, we are going to, from m5.SimObject, SimObject, because we're going to inherit from SimObject, and then we're going to create a new SimObject called my SimpleObject. Again, camel case. Inherits from SimObject. And then we need to give it a few special class variables to make it make all the SimObject magic happen in the background. I need to tell gem5 that the type of this object is my SimpleObject. So this is the name of the SimObject that we're going to create. Let gem5 know where to find the C++ header for this, which is going to be in tutorial my SimpleObject.hh. And then also tell gem5 the fully qualified C++ class for this, which is going to be in the gem5 namespace, my SimpleObject. So in the background, and I'm not going to go into much detail on this at all, but gem5, although this is a Python file, it's not going to be run by Python. It's going to be used by gem5 to create a bunch of auto-generated C++ code. Because this is how we bind things from the C++ models, where we're writing everything in C++, to the Python configuration that Bobby was talking about in the standard library. So with all this, we're kind of telling gem5 the information it needs to do that auto-generated binding between C++ and Python. Any questions here? Okay. By the way, yeah. Okay, let's see if there's anything else I need to say. Okay, so now let's do the C++ header. So now in my SimpleObject.hh, in gem5, we commonly do these if-def guards on header files to get around circular dependencies. So if it's not defined, tutorial underscore my SimpleObject. So we always use this form of the full path as well as the file name for these guards. If it's not defined, defined, and then eventually we're going to do an indef and put our code in between this. So we're going to include params my SimpleObject. So this is one of these auto-generated files by gem5. So if you haven't built this yet, you're not going to be able to find it. But this will be where the parameters for our SimObject are stored. And we'll see that in a bit. And then we're also going to include SimObject.hh, because we're inheriting from SimObject. So we're going to do all this in the namespace gem5. So we recently adopted namespaces. Put everything that you're doing inside the gem5 namespace when you're working. Otherwise, things aren't going to work right. And then finally, we can declare our class. So again, we're going to do my simple object, snake case, or camel case, public SimObject. And we're just going to declare everything in the public space. One thing to note here, since in our Python, we said my simple object inherits from SimObject, we need to make sure to follow the same object inheritance on the C++ side as well. So the C++ and Python, the object inheritance needs to be parallel. So we have to define, I think, just one function here, which is the constructor. My simple object. And it must take exactly one parameter, which is a const params reference params. And this params is a little bit special. So we also have a macro to make things a little bit easier to declare. Using this macro, we'll declare the type capital P params as it will type def that to my simple object params, which you'll see this commonly throughout gem5 as an easier way to get to the params for this, the parameters for this particular SimObject. It's really important that you use exactly this signature in the constructor. Otherwise, you get a very confusing error, which I might show you in a minute. Make sure you use a const params reference. Any questions here? So this is a convenience macro, which will set up a type def so that this params is, yeah, you can see this here. It's using my simple object : params as my simple object params. It's something you see all over the gem5 code base. It saves you like a dozen characters. Very useful, or not particularly useful, I should say. Okay. Last version of this. So we're going to include the header file, my simple object HH, and then we need to, let's also include IO stream, so we can see that it's actually working. Again, in our namespace, gem5. And then define our constructor. So my simple object, const params reference params. So call the constructor for SimObject, for which we need to pass this params. And then let's just print something. All right, just a simple constructor. If you don't want to type all this out, you can look at the complete version in the materials below. So normally I would say don't ever, ever, ever use cout. In a SimObject, we have a different debugging way to do debugging, which will not pollute in all cases. We'll see that in a second, but for now, we'll use cout. Any other questions? Pretty simple so far. Next step is to declare that this is a SimObject we want gem5 that we want to compile. So in the scan script file, there's no extension for this. This is a very strange file. Don't ask me any questions about it. We import star. We declare the SimObject. So say that in the file mySimpleObject.py, we have a SimObject called mySimpleObject. So inside that file, we find a SimObject named mySimpleObject. And then we also say we want to compile the source code mySimpleObject.cc. By the way, I'm using my in front of everything because there already is a simple object in gem5. So I'm using my so the name doesn't clash with that. Okay, so this is kind of a weird build file, but this is how it's done. Questions? Okay, let's see if I'm missing anything. Okay, so now we can actually build it. So if we bring up the terminal, hopefully gem5 has been built, and then we can rebuild. So run scans again, and we will rebuild gem5. So while that's working, and it's going to tell me that I made a typo somewhere, we can create a config script for this. So oftentimes we put config scripts in configs, but you can do it wherever you want. So I'm going to create a new file in configs called runsimple.py. So if you remember back to what Bobby was talking about, so gem5, really underlying, it's just a Python interpreter. So we can write any Python we want. And now that we've created this new SimObject, mySimpleObject, we can create an instance of that new SimObject inside of our Python. So I'm going to be going a level below the standard library and interacting directly with the API that gem5 exposes at the lowest level to Python in this case. So we're going to import M5, which is the lower level library than the gem5 library Bobby was talking about. Then say from M5.objects import star. So we're going to import all of the SimObjects that we've compiled in gem5. We're going to create an instance of a root SimObject. So in all simulations, you have to have a root SimObject, which is an instance of root. And we are not going to be running in full system mode, which is a required parameter. What was that? So it means we're not going to run in full system mode. We're going to run in syscall emulation mode. Some of this is vestiges of old APIs that aren't very good that we still have to follow. So in some sense, I'm going to say, just do it because I say so. So we have to go into the lower level because we haven't extended the standard library to have a mySimpleObject yet. So I wish I had a picture of this. So you have the C++ down at the bottom, and then the SimObject stuff, so what we saw in like the SimObject declaration file, this is exposing that C++ to Python. Then there's a layer above that which takes all those models and then makes them exposed in a more user-friendly way, such as declaring them as processors, cache hierarchies, and memories, and boards. And that is the standard library. And then you can write your run scripts that either use all those libraries in the standard library, or in your run script, you can just use directly the Python that's been exposed via this? So that's what we're doing this time. It's a good question. Okay, so then we are going to add a new member to this root. And it is going to be my simple object. So in gem5, if you have a SimObject, which root is a SimObject, you can add a member to an instance, which is another SimObject. And so we're making my simple object, this instance named hello, a child of root. So you need this tree of SimObjects in there. So any SimObject that you instantiate needs to be a child of some other SimObject, except for root, which is the parent to everything. So after we declare all of our after we create instances of all of our SimObjects, we need to tell gem5, I'm done configuring my system. Please instantiate the system. Please create all those C++ objects from this Python specification that I've made. So you can do that with m5 instantiate. So this line will actually create all the SimObjects. So it's at this point that the constructor for our SimObject will be called. So we could, this is just Python, so we can print whatever we want. So we're about to call instantiate, and then we can say m5.simulate, which will run the simulation loop. And this will run the simulation loop forever until we get an exit event. Let's see if I missed anything here. No. Any questions? Okay. So hopefully gem5 has been built. So now we can run build null gem5.opt and then pass in this run script as our parameter, which was in configs run simple.py. So if we do that, there's a problem. Oh, thank you. Systems are too smart for their own good. So in this output, you can see there's just some stuff that gem5 does. And then it says we printed in our Python about to call instantiate. Then we see hello world from a SimObject. So that actually called the constructor at this point. And then about to simulate. And then when we ran simulate, it just said starting to simulate. And then it stopped. We're going to add an extra line here at the end. Say exited at tick m5.curtick. So ticks are gem5's unit of time. Because this m5.simulate returns an exit event, so we can ask what the exit event reason was. And now if we rerun gem5, so you can see we exited it at tick. Well, that's -1 of an unsigned int because the simulate limit was reached. So nothing was on the simulation queue, so we just reached the end of time and stopped simulating. Any questions? If I want you to take one thing away from this, it's that your run scripts are just Python, so you can write any Python code you want, such as using nicely formatted f strings. Always use f strings. Okay, so that's a basic SimObject. Any questions about making a basic SimObject? Yeah.
Theoretically, could I combine SimObject with standard library object?
You could,
If I wanted the same simulation, you can go
Yes, absolutely. You could combine.
Need to use the M5, or could I?
So you would have to say, if you wanted to combine the standard library objects with your own SimObject, you would have to at least add this from m5.objects import star. Almost everything in the standard library is a SimObject. So if your new model, you can just add that as a child to anything in the standard library and it will work. Yeah. Good question.
Is that because of the second one?
Are we in the terminal? Yeah.
Just curious, I think it's very big number.
Yeah, so the ticks are stored as an unsigned 64-bit unsigned int. So this is just -1. It's the highest. It's the largest possible unsigned int.
Because it was not ISCA.
No, this is because there was nothing in the simulation queue. And initially we put one object in the simulation queue, which is an exit event at -1. Yeah. Okay, so let's make our object. Well, first let's talk about the way we should be debugging, and then we will make our object a little bit more interesting. So in gem5, you can declare, we use a debug flag interface. So the idea is that mostly we use printf debugging, but you don't want to turn on all possible debugging flags because gem5 is hundreds of thousands of lines of code. There's lots of places you want to debug. So we have a way to turn on flags to have certain debugging. So we can declare a new debug flag in our scan script file by declaring a debug flag, and I'm going to call it my hello example. So now we have a new debug flag, which is called my hello example. Then in the CC file, we can include that debug flag, include debug / my hello example. And so this is whatever you called your debug flag, a magic file will appear in debug / my hello example.hh. Now we can replace the standard out with dprintf is what we use in gem5. Pass in the debug flag and then whatever formatting you want. So the second thing is just a normal C format string that you can put anything in there you would like. We could do something like %d 10 or whatever you want. Don't forget to do a new line at the end. Okay, so let's recompile this again. Any questions about the debug interface? There's a number of other functions you can use other than dprintf, although I would say 95% of the time it is dprintf, which I misspelled. Anybody see what I did wrong? Sure looks like it's right. dprintf was not.
Just copy the under debug, right?
I feel like it might be that I built something before. Anybody with a gem5 shirt on see my error?
One of the print statements there was this spurious effect. One of the files.
There's spurious F.
Go to the slot state.
Nobody. Let's see. I think if we look at this, that looks right. I'll copy paste this. Maybe. That looks right. Let me try. Just for fun. All right, we'll try one more time. If this fails again, I'm going to move on. I'm doing something very silly. And I'm not sure what it is. Suggested alternatives. My hello example. It's almost like the Python file? The scan script? That's definitely correct. Did something change in 22 with debug flags? I mean, I tested this last night and it worked. I'll be annoyed if I had to do that. Is it not working for other people? Or is it working for other people? Okay, well, we'll come back to this later, I guess. Deep-printf is... Is that the problem? Anyone remember where deep-printf is? Where is it? You would think so. Is it in debug? I'm not going to. I can't online debug this. Somebody, Bobby, can you try to get my example in 02 simple to build? So this code incomplete here. Try to get that to build. It should work, but it's not right now. Okay, I'm going to move on for the sake of time. And we can talk about how to actually get some interesting timing information out of this. Okay, so before we do that, we need to copy a template from, so I'm going to copy materials, developing, events, my underscore star to source tutorial, and also copy in the Python file, my hello object, and finally copy the scan script. Basically everything but the README file and the run script. Okay, so now in the tutorial we have these files go here. So we have a new SimObject called my hello object. What this is going to do is going to say hello some number of times with some latency between each time that it says hello. And we're going to be able to specify the latency between when it says hello and the number of times that it does it. So in order to do this, we are going to open up the implementation of this file. So now we're going to get a little bit more complicated. So rather than just sending params to SimObject, we're also going to initialize a couple of variables here. So we are going to initialize a latency, which is defined in the header file, but I'll show you that in a second, as well as initialize a number of times that we're going to say hello. So, yep, so latency is, we'll look at the header file here. Latency is a tick, type tick. Tick is however fast you want gem5 to be ticking, whatever you want the quantum, the minimum amount of time for gem5 to simulate is what a tick is. Usually, it's a picosecond. By default, it's a picosecond, and I've never really needed to use anything other than a picosecond for a tick time. So 1,000 ticks is 1 nanosecond. Times left is just an int. Yeah.
Isn't it get set by when we decide the clock? Like,
so tick is different than the clock. Tick is the global tick frequency that you enqueue, like that's the time you enqueue an event on the event queue, which is different than any clock rate that you would have. This would allow you to have multiple objects with different clock rates. They all agree on what a tick is, even if all the different objects have different clocks. We don't use floating point time. We use integer time in ticks. So it's not perfect. For instance, if you want to run at 3 gigahertz, that's 333 ticks per clock, which means that you're going to get off by 1 picosecond for every nanosecond. Okay, so in here, we're also going to add in the header file a couple of things. So this is an event-driven simulator. So we need an event, and we need a function for that event to call. So we're going to add a function for the event to call, void process event, and then an event to actually do it. So we're going to use the event function wrapper, which is just going to wrap around this function that we want to call. We're going to call the event event. So then back in the C++ file, we need to initialize this event. So to initialize the event function wrapper, a function itself, we want to pass the bound function process event. We want this process event to be bound to the class that we have here. So to do that, the easiest way in C++ is a lambda function. So we are going to capture this to bind it to this event or this class and call the function process event. Now, creating an event requires a couple of other things. It also requires a name. So let's use the name for the SimObject, which you can get with the name function, plus event. That's the name of this event. And then I think the other things are all optional. So we've said that every time we execute, or every time this event is pulled off the event queue, we want it to call the function process event on this particular instance of our model. Questions? Okay. So we also have the latency and times left. I'm afraid this isn't going to work because of this dprnf problem that we're running into, but we'll worry about that later. So now we're going to think about what we want to do to process the event. So what we want to do is do this event for some number of times with a latency in between each time. So we are going to, in the event, decrement the number of times we have to do it in the future. And then if we want to do this again, so if times left is greater than 0, then let's add a debug flag so we know what's going on. Oop, wrong one. Sorry. Let me flip my logic. If we're done, if the times list is less than or equal to 0, we're going to say we're done. And then that's all we're going to do. Otherwise, we're going to schedule. So if we're not done yet, we want to do it again. So we're going to schedule this event for some time in the future. So we're going to schedule the event to happen at the current time plus whatever latency we're waiting for. So every time the event happens, until we're done with it, we're going to schedule another event to just do the same thing. Any questions on this? Make sense? Okay, and then the final thing we have to do is we have to make sure to schedule the first event to get things started. So in this special function called startup, which is called the first time you create the system in gem5, the first time you call simulate is when startup is called. We want to kick things off initially. So we're going to schedule the event at latency time in the future. Actually, the absolute time latency. Okay, and then the only other thing we need to do is make sure that this file is declared in the scan script. So we need to expose the SimObject, my hello object. Everything else should be good to go. And then we can rebuild gem5. Which I'm going to bet isn't going to work. Have you figured out the problem yet, Bobby? It's a different, well, I overwrote the scan script file to not do my simple object anymore. Well, now it works. I must have had a silly typo somewhere in my previous example. Must have been a little typo somewhere. This is the problem of doing line coding examples.
Spurious F setting in one of the print statements, but I didn't know enough to interrupt you.
Yeah, I believe you. I didn't see it.
I'm not sure for that program to interrupt someone.
Yeah. I understand. Okay, I'm going to do this, and then we're going to add a parameter. And then I think I will skip the rest of what I was going to do in the name of time. So using this event scheduling thing is essentially how we get all the timing for all of our models. Is picking the right time to schedule the right events. Yeah.
You will cover some of the things we can follow up with.
Yeah. I'll cover a bunch of other gem5 stuff in a moment. All right, so I'm going to copy in from materials, developing the run script to the config directory. And now I can run build, null, gem5, configs, run hello goodbye. Let's check to make sure that file is ready to go. So this looks a lot like what we have before. So we're going to create a my hello object this time, instantiate, etc. So let's see how this works. So if we run it, we don't see anything. Just like before, we saw exiting at tick whatever. That's because we don't have our debug flag enabled. So if you add a parameter to gem5, so it's important to this. So any parameter you add after your script is a parameter to that script. Any options or parameters that you add before the script will be passed to the gem5 binary. So the debug flag is something we want to pass to the gem5 binary. I said it was my hello example. So now, I have a typo somewhere. Again, times left is 10, times left 9. Oh, right. After, so we see at tick 10,000. So we did 10, 1,000 times. We have this printing done firing. So we could also add a dprintf to the process function. Dprintf, my hello example, firing at some tick. Or actually, let's say, some number left times left. So I'll show this in a second. Before I want to add, so you might want to add a parameter so that from your Python, you could change the latency and the times left. So to do that, we can go to our SimObject description file and add parameters. So we're going to say the time to wait between fires, between the event going, param.latency. And we're going to add another parameter, which is the number of times that we want to do it. So these parameters, you always have to do param.atype. Latency and integer are two types of parameters. A latency parameter you can specify in terms of human readable latency. So you can say 1 nanosecond, 2 seconds, 1 millisecond, and it will be automatically converted to ticks, depending on whatever the tick rate is for your simulation. An int is just an integer. There are lots of other parameters as well. You can also use a SimObject, another SimObject as a parameter to some SimObject. Then you have one required argument, which is a help string, so something to explain to the user what this parameter is for. And then optionally, you can provide a default. So in this case, I've provided a default number of fires to 2, and no default for the latency. So the fact that the latency doesn't have a default means you're requiring the user in their Python run script or in the standard library to specify this parameter always. And then in our C++, we can grab these parameters from this params object. So we can do params dot number, or what did I call it? Time to wait. for the latency and params dot number of fires for the times left. So whatever you called the parameter in your SimObject description file is what the member is in this params class. Okay. So I'll rebuild this real fast, and we can look at how this works. If you go through the rest of the completed section, it shows how to connect these two objects together and a little bit more complex model of something that has some fixed bandwidth to see how long it takes to transfer something across a line. There's also a full cache example if you go to the gem5 website. See how to make a cache. Questions? You can use GDB with gem5. Make sure you use gem5.opt, not gem5.fast, because gem5.fast doesn't have any debug symbols. Gem5.opt does have optimizations, which sometimes tricks GDB. And so if you need to get rid of optimizations, you can compile gem5.debug, which has no optimizations, but it has debug flags. But gem5.debug is much slower than opt. Yeah, like 5x slower or something. Waiting for something to compile is like waiting for water to boil. I assume it's going to happen sometime soon. There we go. Okay, so if we rerun this, it gives us an error, fatal. Hello.time to wait without default or set value. So we had a parameter that didn't have a default, so we got an error saying that it didn't have a default, didn't have a value set. So we can go back to our run script here, and we can set the parameter. So for instance, we can say the time to wait is, I don't know, what do we want? 10 microseconds. Again, this is a user understandable thing since it's latency. And so you can do this either in the constructor by passing named parameters, or you can also do it explicitly, say if we have the, what did I call it? Number of fires. Number of fires, 7. You can also set the members of your instance as well. So now we can see that it fired 7 times with 10 million ticks in between, because 10 microseconds is 10 million ticks. Any final questions about parameters? Okay, cool. So I'm going to stop back to PowerPoint. So rather than going through all this, I'm going to skip over that and just talk some about a little bit of everything else in gem5. Okay, so I want to talk about some of the main models that you might be using as you build your system. So the big power of gem5 is not only can you use it to make a model for whatever you want to model, but it also has a large number of models that you can use to plug into your system. So let's talk briefly about caches. So there's 2 kinds of cache models in gem5, what we call the classic caches and Ruby caches. So classic caches just have one model, one SimObject, which is cache. And you can configure this cache to be any level in the hierarchy. It has replacement policies, prefetchers. You can set it to be mostly exclusive or mostly inclusive, although not just one or the other. One of the downside of the classic caches is that it has a coherence model, but it's kind of faked. So there's magic that they're doing, the caches interact with each other to keep them coherent. It'll give you correct results, functionally correct results when you run, but if you really care about thread interactions and coherence, the timing results will not be particularly high fidelity. This is really good for functional simulation. It's also good for simulating things if you don't care that much about multi-threaded or coherence. It's also got a quite simple interface to interact with the rest of the system, and it's really easy to configure. So like the private L1 hierarchy that Bobby was looking at before was just a single cache. Doing this more complicated hierarchies is simple to do, but again, not particularly high fidelity. If you care about high fidelity caches, you should be using Ruby and Slick. So this models a very detailed cache coherence protocols. In fact, it can model many different kinds of protocols. It is actually a complete domain-specific language for specifying state machines for caches. And so you can write your own coherence protocols in this as well. So that Slick is our language, and then Ruby is all the models that Slick uses to model like the data store, the tags, etc. We have lots of different protocols available. A 3-level protocol, 2-level protocol, all sorts of different protocols, GPU protocols, region coherence protocols, all sorts of things. If you want to learn how to create your own protocol, check out Learning gem5 Part 3, which is on the website. It also has very detailed on-chip network. It models like a 3-stage router. It converts the messages into flits. It models serialization on the lines, etc. But the really nice thing is that the protocol and the on-chip network and the topology of the network are all completely separately configurable. So you can have any protocol work with any topology, but it becomes very complex to set up your configurations. One of the reasons why we have the standard libraries, we hope we can hide that kind of complexity within the standard library. Though, to be honest, we're not doing that too much yet. So to give you an idea, Ruby is just this big black box that kind of connects everything together. They're connected via ports, not too important. And then on the network side, again, the network is a big black box. You connect all your Ruby controllers into the network, so it can be any topology. So we also have a relatively new cache model in the last year or two, which implements the AMBA-CHI specification. Not completely, but with enough to get a lot of things to work. This is based on Ruby and Slick, so it's really high fidelity. But the cool thing is that it's just one model, again, one cache, which will be configured to be any kind of cache in the system. Or it's one cache which is configurable to be any kind of model that you need. So it's kind of like the classic caches in that you can reconfigure it pretty easily, but it's like Ruby that it's high fidelity. I think you'll be seeing more and more of these standard library cache hierarchies implemented using CHI because it's both flexible and high fidelity. Okay, so that's caches. We move to memory. There's a memory controller in gem5, which is event-driven. It's high fidelity, but it's not cycle accurate. It's not meant to model every single cycle that's happening in DRAM, but it gives a pretty well-validated results for a lot of different DRAMs. So we have DDR3, 4, LPDDR 2, 3, and 5. We now have HBM pseudo-channel support, which I think Ayaz is going to talk about at the workshop, as well as HMC, NVM, and other things. Gem5 can also connect to other DRAM models like DRAM Sim3 and DRAM Sys. All right, CPU models. Sorry, I'm flying through this. Interrupt me if you have a question. So the cool thing about Gem5 CPU models is that they are ISA independent. So you can create an ISA, and that will work with any CPU model. You can create a new CPU model, that will work with any ISA. So this API between the ISA and CPU model has been carefully defined. We support a bunch of different ISAs. You can look in source Arch. We support GPU ISAs, new CPU ISAs like RISC-V, and old CPU ISAs like. They're not all equally well supported. ARM and RISC-V are supported better, and x86. Each directory contains an ISA definition. I'm going to skip over all the details about how to create ISAs. So gem5 has a number of CPU models. As I said, we have a flexible CPU interface. So we have the atomic model, which is just a functional only model, but it can be used to warm up caches. We have a timing simple CPU, which is a simple single cycle CPU, except for memory operations. So everything takes a single cycle to execute, unless you go to memory, and then it has to wait for memory to come back. And in fact, I don't think it can even have multiple outstanding requests to memory. Then there's the O3 CPU model, which is a full out-of-order model based on Alpha 21264. So take that as you will. If you want a model, if you're looking for the performance of a modern i7, the O3 CPU is not what you're looking for. If you're looking for the performance of an out-of-order processor from, 2001, 2002, it's got you covered. Unfortunately, we don't have a really high performance out-of-order model right now. Great contribution if anybody's interested in contributing it. We also have the minor CPU, which is an in-order model. This is pretty high fidelity. It's modeled on something like an A53 or an A55. And at some point, I think it was actually validated against those systems. It works well for RISC-V and ARM. It has not been fully tested with x86, although I think it works for x86 as well. Then we have the KVM CPU, which actually runs, you can use this for fast forwarding, and it uses your native hardware acceleration to run at native hardware speed. So I briefly mentioned this. So there's different kind of memory modes. So timing is used for simulation if you want to get timing information. Atomic doesn't give you any timing information, but you can use it for fast forwarding. So it'll functionally execute, but that's it. And then atomic non-caching, which is kind of like the fast forward, except it doesn't even go through the caches, so you can't warm up caches. We also have lots of devices. This is a full system simulator, so we can boot Linux. And so to boot Linux, you have to have devices in order to get things to work. So we have like a full GPU model that supports GPU compute instructions. So if you want to run whatever AMD is calling their GPU compute library now, you can run it on, OpenCL, or you can use it. You can use CUDA if you hippify it. AMD has lots of terms. But it supports ROCm 4.2, I believe. And actually, just in this release, we have full system support as well. So you can boot Linux, use AMD's GPU driver, and interact with the GPU. We have lots of other devices as well, including Ethernet, IDE, and VirtIO for doing virtualization. Most of these devices are functional only, because usually you don't care about the performance of the devices. But adding performance models for these devices is relatively straightforward. And finally, I want to say something about contributing to gem5. So we use Garrett for our code review. You can look at the contributing.md function to give details about how to do this. Everyone is welcome to contribute. We love contributions as well. And I was going to go through some details on this, but I think I'll skip over it because it's already like 10 after 12. Skip over all of this. Okay, so caveats. Take what I'm saying here with a bit of a grain of salt, and definitely take results you get from gem5 with a grain of salt. gem5 is a tool. It's not facts. It's not hardware. And most of the models within gem5 have not been validated against any real hardware. So make sure you're careful about how you use results from these models. not only are the models not validated against hardware, but the parameters, oftentimes the defaults are meaningless. So you need to go through and be more careful. We're trying to improve this with a standard library, and I think you'll be seeing a lot more from us about validated configurations for gem5 in the next few months. But just be careful if you're not using something that we call validated. And of course, there are bugs. If something doesn't work in gem5, it's probably not you, it's me. It's probably not that you're doing something wrong. It's probably that gem5 has a bug. We've gotten a lot better, a lot more stable over the past 3 years, but there's still bugs in gem5. And finally, getting more help. So the main gem5 website has all of our documentation. Up in the upper right, there's a drop down that says documentation. The gem5 mailing list is primarily where we have been doing communication with users and answering questions. However, I am announcing today that we have a Slack. And so if you can real quick write down that URL, you can try to join our Slack or join us in the gem5 workshop, and I will show this again. And we'll advertise the Slack much more widely and put it on the website and stuff soon. And also we have an issue tracker. If you find a bug in gem5, please let us know by opening an issue on Jira. Okay, that's it. Sorry, I rushed through that at the end, and I'm sorry to keep you past the beginning of lunchtime. But are there any questions or anything? Can you change the CPU model during simulation? Somewhat. So Bobby was talking about switch CPU, or switching the processor. So in some cases, you can switch from a high fidelity or low fidelity model to a high fidelity. Sometimes back and forth, sometimes not. So what I usually do in my simulations is pick a region of interest, then fast forward to that using the KVM CPU, and then switch to a detailed CPU to look at the region of interest. Yeah.
To understand what made the memory model not cycle accurate, is it?
So it is cycle level. It is, we enqueue an event for 5 cycles in the future, but it is not accurate to any particular DRAM. So we did not write RTL for a DRAM chip or for a memory controller. Yeah. Yes, we will make today's slides available somehow. They're actually, I put links in the YouTube comments, but I don't know how helpful that is for you all. What's the easiest way for me to give you the slides?
I've been asking people who wanted the slides to send Davis our research at gmail.com an email.
Okay. So we can do that. I'll also, on the web page, I'll put a link as well. No, I'll put a link on the tutorial and workshop page. Yeah. We'll put them up there. Any other questions?
Ruby is something that you guys maintain? Is that internal?
Ruby is internal to gem5, yeah. It's not separate anymore.
Your vision going forward is to
I would love it to be that way. I cannot say with any certainty that it will ever be that way. The biggest downside to Ruby is that it's slow. It slows down simulations significantly.
in terms of like simulation accuracy,
It's much more accurate
it's more accurate.
than the classic caches. Yep. Classic caches are okay if you're modeling something that's a hierarchy of crossbars in relatively small caches. But as soon as you want to do anything that's like a mesh or want to do a cache coherence protocol that isn't very simple, then it's not the right tool for the job. Okay, great. Well, thank you all for your attention. Hope to see you here in the afternoon for the workshop.
All this is open source. We can pick up your processor model and extend.
Everything is open source. Yep. And it's licensed under something that's like BSD 3 clause. So it's also very easy to use in industry as well.